We want to verify Green's theorem in a plane. For that purpose, we need a region enclosed by a closed curve. In this case, we are given y square equal to x and y equal to x square. Let us draw those two curves. So we have x-axis, we have already drawn x-axis, and then y-axis. We take a point 1, 0 on x-axis and 0, 1 on y-axis. Now, first of all, we need to draw those curves as per the question. We have y equal to x square. Y equal to x square, that's a parabola, and it is such that y remains positive or 0, whatever be the value of x. So we have y equal to x square. That's a parabola. Then we have second curve is x equal to y square. First we have y equal to x square, that's a parabola. It is symmetric about y-axis. The second parabola is y square equal to x, that's a curve symmetric about x-axis. So we have y square equal to x, that's a curve symmetric about x-axis. So we have obtained a closed curve that encloses a region. So we have to verify Green's theorem in this region. Now, having a closed curve is not enough. First of all, we got a closed curve, but having a closed curve is not enough. We need direction as well. And not only that, we need to give anti-clockwise direction. We take a point P on the curve. Let A be the point of intersection point of those two curves, and we take a point Q on the other curve. So we obtained a closed curve OPAQO. As I said earlier, we need to give a direction. Not only that, we need to give an anti-clockwise direction. We move from OPAQO. So we have obtained a closed curve and we have given an anti-clockwise direction. Further, we need to have a region inside that closed curve. So we got a region inside this closed curve. Now let us write the formula for the Green's theorem. Formula that we need to verify. By Green's theorem, we are writing the formula that we need to verify. So by Green's theorem, integral over closed curve. We have already obtained a closed curve, that is OPAQO. F1 dx plus F2 dy equal to integral over region. Integral over region. What is that region? Region is exact region that encloses that closed curve. Del F2 del x minus del F1 del y dx dy or dy dx, that will depend on our choice. Let's write dx dy. Now, as per the question, we have integral over closed curve. In our question, we have integral over closed curve 3x square minus 8y square. 3x square minus 8y square dx. In our question, we have 3x square minus 8y square dx plus 4y minus 6xy dy. 4y minus 6xy dy. That's what is given to us. If we compare these two, clearly we have f1 equal to, or rather we should choose f1 equal to, we choose f1 equal to 3x square minus 8y square, and then f2 equal to, if we compare these two, we have chosen f1 equal to 3x square minus 8y square, and then f2 equal to 4y minus 6xy. So we have chosen f1 and f2. Now we observe that it is easier to evaluate the right hand side, so we evaluate the right hand side. So we compute right hand side of Green's theorem. Right hand side of Green's theorem is integral over region del f2 del x minus del f1 del y dx dy or dy dx, that we need to find out, or we are free to choose dx dy or dy dx, that is up to us. So right hand side is given to you, but let's compute this quantity del f2 del x minus del f1 del y. Del f2 del x minus del f1 del y equal to del x of f2. What is f2 here? 4y minus 6xy. 4y minus 6xy. What about f1? f1 is 3x square minus 8y square. 3x square minus 8y square. Now, if you are differentiating partially with respect to x, then you will regard y as constant. So, del x of 4y is 0. Again, if you are differentiating partially with respect to x, you will regard 6y as constant. So, minus 6y is constant. Then you are left out del x of x, that is just 1. Again, if you are differentiating partially with respect to y, then you will treat x as constant. So, del y of 3x square is 0. Lastly, del y of 8y square is 8 into 2y. That will give us 16y minus 6y, that is equal to 10y. Therefore, RHS equal to integral over region del f2 del x minus del f1 del y dx dy, and that turn out to be 10y. 10y dx dy or dy dx. Let's write dy dx. Now we need to exactly cover the region, so let's look at the region once again. Region is the region enclosed by the parabola y equal to x square and y square equal to x. So let's try to exactly cover this region. We can change y from y equal to x square to y square equal to x. Then we will be exactly covering this region. But in that case, we will be covering this region as well. So what we'll do is we'll change x from 0 to 1 and y from y equal to x square to y equal to root x. Let's do it. So reason is nothing but we need to change x from 0 to 1. This reason can be obtained by just covering x from 0 to 1. Your x is changing from x equal to 0 to x equal to 1. And then y is changing from y equal to x square to y equal to root x. Y is changing from y equal to x square to y equal to root x. Then y dy dx. dy, and lastly we will integrate with respect to x. Now we know that integral of tan y with respect to y is tan into y square by 2. Your y is changing from y equal to x square, y equal to x square to y equal to root x. Lastly, we have to integrate from x equal to 0 to x equal to 1. We can cancel 2 and 10. And so we have 5. When you write y equal to root x, y square will be x. When I write y equal to x square, y square will be, we are writing y equal to x square and hold this whole square as it is. So upper limit y equal to root x, so y square will be x. Lower limit y equal to x square, y square as it is. Your x is changing from 0 to 1 dx. 5 we can take out of integration. Integral of x is x square by 2. Integral of x to the power 4 is x to the power 5 by 5. We can write limit of integration. 1 by 2 minus 1 by 5, that is 3 by 10. If we simplify it, we'll get 3 by 2. Compute left hand side of the Green's theorem, that is equal to integral over closed curve 3x square minus 8y square dx plus 4y minus 6xy dy. Once again, 3x square minus 8y square dx plus 4y minus 6xy dy. Now closed curve consists of two parts. The curve C is a closed curve as you can see in the figure. C is a closed curve OPAQO. OPAQO. C is a closed curve OPAQO. So we evaluate along OPA first. Let us do along OPA. Along OPA. We observe that along OPA, y equal to x square and x is changing from 0 to 1. Along OPA, we observe that, comma, y is equal to x square, comma, x is changing from x equal to 0 to x equal to 1. Therefore, integral along OPA 3x square minus 8y square dx plus 4y minus 6xy dy. Once again, 3x square minus 8y square dx plus 4y minus 6xy dy equal to x is changing from x equal to 0 to 1. So x is changing from x equal to 0 to x equal to 1. And the value of y is equal to x square. So we change, instead of y, we will write x square. Rest of the thing we will copy as it is. Instead of y, I'll write x square. Rest of the thing we copy as it is. Dx as it is. Instead of y, I'll write x square. Instead of y, I'll write x square. Rest of the thing I'll copy as it is. For y, instead of y, we have written x square. Rest of the expression we copy as it is. What about dy then? Since y equal to x square, dy must be equal to 2x. 2x dx. Now let us compute it. We need not write dx twice. Now 3x square, if you integrate with respect to x, you will get 3 into x cubed by 3. X to the power 4, if you integrate x to the power 5 by 5. 4 into 2 gives us 8. X square into x gives us x cubed. So 8 into x to the power 4 by 4. X into x square gives us x cubed. X cubed into x gives us x to the power 4. 6 into 2 gives us 12. X to the power 4, if you integrate it, you will get x to the power 5 by 5. X is changing from 0 to 1. Let us compute it. We have 1 minus 8 by 5 plus 2 minus 12 by 5. That gives us 3 minus 20 by 5. That is 3 minus 4. That is equal to minus 1. Okay, that's along OPA. Now let's do along AQO. So far we have evaluated the integral along OPA. What about along AQO? Let's write it down. Along AQO, if you look at the curve AQO, you observe that y square equal to x or y equal to root x. So in AQO we have y equal to root x. Now remember, we are moving in anti-clockwise direction and we are moving from A to O. So x is changing from 1 to 0. Once again, x is moving as you moving from A through Q back to O. We are moving in anti-clockwise direction and we are creating a closed loop. So x is changing from 1 to 0. Along AQO, y equal to root x, comma, x is changing from 1 to 0. Therefore, integral along AQO f1 dx plus f2 dy equal to, let's write it in the next line, x is changing from 1 to 0. X equal to 1 to 0. f1 is your 3x square minus 8y square. 3x square minus 8y square. f1 is your 3x square minus 8y square. Okay, let's write it as it is. Dx f2 is 4y minus 6xy. 4y minus 6xy. But as we have said, y equal to root x. So let's replace y by root x. Instead of y, we'll write root x. Instead of y, we'll write root x. Instead of y, we'll write root x. So dy will be equal to 1 by 2 root x dx. Rest of the expression will keep as it is. 3x square minus 8y square. Instead of y, we are writing root x. Dx we are copying as it is. Instead of y, we are writing root x. Instead of y, we are writing root x because along the curve AQO, y equal to root x. Dy equal to 1 by 2 root x dx. And x is changing from 1 to 0. X equal to 1 to x equal to 0. Let's solve it. So we have 1 to 0, 3x square minus 8x dx plus, we can cancel 2 root x, so you are left out with 2 minus, if we cancel 2 root x, we are left out with 3x dx. Since we are writing dx twice, let's write the integral twice. Now we can simply compute it. If we integrate 3x square, we'll get 3 into x cubed by 3. 8x, if you integrate it, we have 8 into x square by 2. Limit 1 to 0. 2x minus 3 into x square by 2. Upper limit, when we write 0, we'll have 0 only. 3 gets cancelled. 2 into 4 is 8. upper limit, when you write 0, we get 0 only. Lower limit, if I write 1, then you have minus 1 minus 4 minus 2 minus 3 by 2. That is equal to 3 minus half. That is equal to 5 by 2. So, let's combine it. Along AQO, we got it 5 by 2. Along OPA, we got the integral equal to minus 1. Now, the curve consists of two portions. The closed curve is made up of a let's look at the closed curve once again. OPA and AQO. Closed curve is made up of OPA and AQO. Okay. Made up of OPA and AQO. And so integral over closed curve f1 dx plus f2 dy equal to integral along OPA f1 dx plus f2 dy plus integral along AQO f1 dx plus f2 dy. Along OPA, we have computed it and we got it minus 1. So, this is equal to minus 1. And then AQO, we have computed it. Along AQO, we have computed it and we got it equal to 5 by 2. So, minus 1 and then 5 by 2. If we add it, that will be 3 by 2. So, left hand side equal to right hand side and we have verified Green's theorem.